Hello and good morning, everyone. It is 10 past 10 in room number 10. Look at that. I hope you've had a good start yesterday and this morning. My name is Axel Fontaine, and for the next 50 minutes or so, we're going to talk about Majestic Modular Monoliths. So just two words about myself. So Axel Fontaine, originally from Belgium, living in Germany these days, been in the industry for about 20 years. I'm a Java champion. Some of you may know me through my open source project, Flyway, for database migrations, or the company I run, which is called Coldbox Fuse. We do deployment of continuous deployment of applications in the AWS cloud. So this is something we're not going to go too deep in today, but let's get started. So 50 minutes is not a huge amount of time either, and we have a relatively short period of transition here, only 10 minutes between talks. So if you do have any questions, I would like to please ask you to hold on to them until the end. I'll be around. We'll have plenty of time to discuss them after the talk. During the rest of the day, I'll be around the conference the whole day and immediately afterwards as well. So and then we'll discuss them there. But we won't be this way. We won't be holding back people that want to move on to the next session in time. So, talking about time, let's step back a little bit. What I have here is a picture or a drawing of Pope Sixtus V. And in 1587, he made quite an important change to how the Catholic Church was working. So this is long, of course, before the time of Karol Wojtyla, but it is, he made a change. He introduced a new office called the Devil's Advocate to basically give somebody the chance to provide counter-arguments to the canonization of somebody on their way to sainthood. And this is a little bit the aim of this talk also. It is primarily there to try and generate a little bit of an opposition to the dogma of microservices, which we've been hearing for the last couple of years. Hopefully provide you with some food for thought and maybe some interesting ideas to take home of how maybe a more balanced approach to things could also be something that could be quite beneficial for the context you work in. So, if we kind of look at the whole aspect of producing code and running it on the machine, it all starts with the developer, and eventually we write some code in our IDEs. We have some source code that will compile to down to some machine code, which eventually gets executed by the processor. And if we look at this chain here, these different steps, as the size of code increases, there is a very clear place where the bottleneck is. And trust me, it's not on the right. You can throw an infinite amount of ones and zeros at the processor and it will just keep on executing them. But for us, as the size of code increases, it becomes harder and harder to comprehend it. And that is really the reason why I think in our profession, if we kind of look at what we're doing when we say we write code, it's a bit of a misnomer, because at the end of the day, a lot of the work we do is understanding what's out there, is trying to figure out in the existing system which changes do I need to make to implement this new functionality or fix this bug. So it's a lot of time spending trying to understand, and once we know what we do, then we actually do the typing and we make the adjustments to the source code as needed. So this is really, if you kind of look at the read-write ratio here, you gotta start and optimize for the things that make sense. And in this case here, it's optimizing for understanding, it's optimizing for reading the code. Now, if we look at this here, what can we do to do that? So the first thing we do is we can add structure to our code by splitting it in individual source files where we have different classes. We can raise the level of abstraction that we have to make it easier to talk about things, to have an easier understanding of that, so that we at the end can reduce the load on our brains, so that we can really then grasp even very large complex systems and hold them within our heads, which would not be possible otherwise. It is all about seeing the forest through the trees. So what kind of tools do we have at our disposal for this? First of all, at the most basic level, we have methods which we can use in a class to divide. Then we have multiple classes themselves. Then we can group these classes into packages where it makes sense. And then we can group these packages into modules. And eventually, we can group these different modules in individual applications. And this really, at the end of the day, is the architecture of our application. It's how we kind of structure and how these different levels of abstraction interact, what their relationships are. This is really what defines the architecture of our application. Now, in terms of architecture styles, if we look at what's being predominantly talked about these days, then there's really two terms that comes to mind. The first one is the monolith, and the other one is microservices. Now, if we were to look at different pictures of how to kind of describe those based on the conference agendas of the last 3 and 4 years, it would look more like this, where basically monolith has not had a very favorable role to play. Let's say here, and microservices are presented as the new awesome thing. But who's pushing the microservices? If you kind of look at where a lot of the tooling and frameworks are originating from, it's really coming from companies like Amazon, like Netflix, like Google, like Twitter, and these companies really, for them, I think it is really a fantastic solution. But let's take a step back. How similar are these companies to the company you work for? These companies that have thousands and thousands of engineers working for them. How many developers do you have working at your company? Do you really think it's very closely related in terms of capacity that you have available to what they have? Do you really think you can use the same tools? Because we can really look at a bit of wisdom here. If you fetishize and cargo cult the infrastructure required by companies with literally 10,000 times your traffic, you will not have fun. And there is a lot of truth into that. Just this morning, I went on the job website from Amazon, just to give you a bit of an idea of the size of these companies. So this is the jobs website for Amazon, and I did a bit of a search. So you can see here 6,430 open positions. But you'll tell me, well, Axel, but Amazon, they have a lot of warehouses, and they have a lot of people doing manual work. Well, wait a minute, and let's see. Let's scroll down a little. What do we have here? Oh, 6,430 open positions. That's only for AWS. It's not the rest of Amazon. Yes, but there are a lot of salespeople on AWS, and there's a lot of business managers. So let's have a look. Let's dig deeper. Oh, 3,800 open positions in technical roles for software development, software architectures, and engineering on AWS alone. Now compare that. That's just the open positions. That's the people they're looking for now. That's not the total size of the organization. Compare this with the amount of people that you have available in your company. And do you really think there is a comparison now? Okay. So if we have our monoliths on the one end and our microservices on the other, let's look for maybe a more neutral term to describe them. So I like to think of a monolith as an integrated system and microservices as distributed systems. But then again, distributed, I think we heard that before, didn't we? What's the first law of distributed systems again? Right, what does Martin Fowler say? My first law of distributed object design is don't distribute your objects. And I think we have the same thing certainly happening here at the system level. So how do they compare? Monoliths, microservices, let's have a look. Monoliths have the very nice property of being quite simple. You have one artifact where everything is contained that you can deploy all at once to the environment of your choice, and you're done. Microservices, you have different individual artifacts for each individual service that you need to deploy. On the other hand, with the monolith, because there is only one, there is the chance to kind of create a mess inside and that it's all tangled up. I think we've all lived through those projects where it becomes very difficult to understand, to refactor. That's really a clear risk that we have there. Microservices will tend to be younger at the individual service level, at least. And so there is also a smaller size, at least in theory, for each individual service. So we've got a clear focus there with individual units, which is quite a nice thing. On the other hand, when it comes to actually communicating between different parts of these two, then the monolith is actually quite fantastic. We just do a simple method call. It's very, very fast, very reliable, directly in memory. There's not much that can go wrong. On the other hand, microservices, we introduce the network in between that can fail. We have latency in between. So we have all kinds of things where we may need to be introducing retries and handling all kinds of failure conditions. Parts may not be available that were there before. So more things to think about. Because again, in talking in terms of availability, the monolith, the nice thing is, it's always all there. All the parts are deployed at once. They're always available. There's nothing that can break away or go down for a shorter amount of time, or that is currently not available. Versus on the microservices side, we do have those risks. So we have tools to mitigate them. We introduce things like service discovery in combination with internal load balancing and circuit breakers in case we need to temporarily disable access to a specific subsystem because it isn't behaving properly, for example. The monolith is also something that is quite easy to refactor. It's all in your IDE. The IDE knows all the references of all your methods, so if you're not happy with the name of a method, you just rename it and all the references are adjusted for you, not much to do. If you want to move things around, you have very nice automated refactoring support. Once you move across the system boundary, it's not that easy anymore. The interfaces are much more difficult to adjust there. There's something that you have to think about very, very carefully because it becomes very expensive just to figure out who your consumers are. After a while, you may not know anymore within a larger organization who exactly is consuming which API endpoint with which arguments. This is something that is much more difficult to keep track of versus in a monolith, the IDE can simply do it for you. Now, in terms of scaling, the monolith is a bit of an all or nothing thing. You kind of scale the whole thing vertically up or down as you need to. Versus the microservices, there we have the nice property of being able to turn the dials individually on each service, where some service may need additional capacity, so we can just scale that without scaling the rest of our infrastructure. The monolith will typically use one database, very often a relational database where everything will be persisted in. The microservices world opens up more possibilities there, where each service can and will use the persistent solution that it needs, whether it's a relational database here, or document store, or key value, or whatever you need there. But the good thing of using just a single database is that it comes with a very powerful thing, ACID transactions, where you have the guarantee that when you actually commit something, it's actually there, and you're able to cleanly roll back in case of error as well. Versus on the microservices side, you're dealing with eventual consistency, where you actually have to solve the same problems. The difference is that now, instead of having the database system solving it automatically for you, you have to rewrite some of this logic yourself in code to compensate for those events. Now, the monolith, because it's just one unit, will be deployed on one technical platform, like the JVM, for example, versus microservices, where you really have a choice of deploying each individual service on the technology that makes most sense. If you have some aspect of your architecture that should be written in Node, because that's a very good fit, and you can do that, and you can run other parts on the JVM perfectly fine. A risk, of course, of having everything together in the monolith is that you have to deal with dependencies and their versions and potential conflict and the whole thing that we know as jar hell versus microservices where it's not really such a problem because it's nicely isolated. You can use different incompatible versions of the same library in different services, not a problem. This is all nicely working there. And so if it comes to dealing with team sizes as well, monoliths are really something that offers rather limited parallelization for teamwork versus microservices, which offer you very nice division of labor, where you can then map them. And we've all heard of Conway's law, where you can then have individual teams taking over individual services. That's a nice boundary that's often being used in practice to divide work there. So these are really things that kind of differentiate monoliths and microservices. So it's not really black and white. It's not really that one is perfect and the other is really total garbage. It's a trade-off. And if we kind of look at this, we can really see that monoliths are actually a fantastic fit for small organizations, simple applications. They are really a perfect fit for that. They don't bring any additional unnecessary complexity to the board. It's all just what you need and not more. But as you grow, you will run into some of the issues we discussed on the previous slide. And so for large organizations and complex applications, the microservices world is actually offering fantastic solutions with great division of labor, nice technological independence between individual services. It's actually quite a powerful thing. But is there room for something in the middle? So without further ado, let me introduce the distributed monolith. No, just kidding. It's very easy to end up at something like this, but don't try this at home. It is something that will actually naturally evolve over time to something like that. So you have to actually pay a lot of attention not to get there, because if you pick your interfaces too early between different services and the match isn't perfect, then you start to get into situations like that. Or if you work in an organization where each team is responsible for a service, but then some new functionality needs to be implemented, and the team that really should be doing it doesn't have time in the coming months, so somebody else implements it, and that's how you start kind of building up entanglement like that. So these are very real scenarios that I've seen in my consultancy life, so just be careful there, but we have a different way, luckily. If we look at the nice properties of monoliths and the nice properties of microservices, we can actually combine them and have something which we call a modular monolith. And in fact, it provides so many advantages that I even like to call it a majestic modular monolith. So it is really all about adding the necessary structure to a monolith to make it manageable. Now, when we talk about monoliths, very often you would get a picture like this, but that's not really fair, to be honest with you, because if you kind of look at most of the monoliths out there, their structure is much closer to this, where you have some kind of layered architecture in place. It's not total chaos. There is some kind of layered architecture in place where you recognize things like controllers and services and repositories, and they'll all access a database, and they'll have dependencies in a specific order where controllers only talk to services, and they only talk to repositories, and they talk to the database. So this is actually quite common, even in monoliths that people would say would be difficult to refactor or work with. In fact, this structure is so common that it's also part of the scaffolding that's being generated by a lot of frameworks for you. So if you have things like JHipster or Rails or Play or Grails, they will all kind of generate this kind of structure automatically for you. So this is something that's very widespread and works quite well at a small scale also. But as you start increasing the size of your application, it becomes more of a problem. So let's say, for example, you have different large functional areas where you would have something for managing customers and managing invoices and managing payments, and those are kind of the typical flows that you would have where, again, you go from controller to services to repositories to database, and that's all kind of nice and well as long as it stays like this. But the reality is that as you start dealing with slightly more complex requirements, there are dependencies that start to creep in between these nice silos that we have there. And that's where things get really complicated, to kind of take care of being able to keep in your head which relationships are actually happening there and how you can still keep track and refactor and deal with those. So luckily, we have some tools available to the rescue. This famous book by Eric Evans, Domain-Driven Design, who's read it, just out of curiosity? So we have about a third of the room. So the book's about 15 years old, or 14 to be exact now. So it is slightly showing its age when you read it. So you have to read it with a certain historical context. And they're talking about XML as being the new and upcoming thing. So it just kind of places you a bit in kind of the time frame that this was written. But it carries a very large amount of very good ideas for structuring code. And one of them is the aggregate. Is basically defining a group of functionality that is very cohesive in itself, where it is nicely isolated from the rest, and you have some kind of root from that aggregate where you can then access the rest from. And so in this case here, this would be, for example, the customer object itself, and then the individual properties of the object, and that type of business logic would be hidden inside the aggregate and not visible to the rest of the world. And so if you kind of think in terms of aggregates here, we can start modeling the dependencies between them. And so the nice thing here is, if we kind of looked at, for example, to make a payment, you need an invoice. To have an invoice, you need a customer. We can kind of create a nice acyclic directed graph of our dependencies here. And when they're creating this graph, we can look at stability of individual concepts. And so it is quite important to look at putting the most stable concepts at the bottom. Because if we look here, for example, if we're going to be making some changes to the customer, it will affect the whole pyramid that builds on top of it. So it will affect the invoicing, it will potentially affect the payment things, versus on the other end here, if we just make a change to the payment side of things, there will be zero effect on invoicing, there will be zero effect on customers, because we have our dependencies nicely structured like that. So you look for stable and unstable concepts in your system, and you make sure that the unstable ones depend on the stable ones and not the other way around. This is really a very important guiding principle when thinking about which direction dependencies should flow in. Now, in terms of module boundaries and looking at where you really want to draw the line and the structure there, I think the primary thing to look for is highly cohesive blocks of functionality, something that naturally fits together and that is uniquely well suited to be kept together. You also want to have low coupling to the outside world, so that you really have something that you can isolate nicely from the rest. You want to think carefully about what you expose, and that should be distilled down to an API. Just like you would for services where you would have a REST API, the same happens here at the code level for an aggregate like that in a module. You define a very clear API, and that is the only way other modules will be able to access it. So typically you will have to expose things at the aggregate root level there for that. And the implementation becomes something that is fully private. So there is nobody from the outside world that is able to access it. This is really something that helps reduce the overall complexity of the system and reduces also for you the cognitive load of trying to understand the big picture, seeing the forest through the trees. Depending on the API and not on the implementation will be something that will require some adjustment, probably in the way some of the systems are written. So it takes a bit of work to kind of really figure out what exactly should be part of the API, and then once you've kind of defined that, you stick to it. And then you get to a picture like this, which is really quite nice, where you have the dependencies, and again, only on the APIs of other modules, never on the implementation of those modules. That remains fully private. Now, in terms of isolating code between those different modules, we do have a few tools at our disposal as well. So the first one really we can do is stick things in a separate package. Excuse me. Where you would have one package per module, and it would all still be within the same jar file. It would be versioned together with the rest of the application, and they would all still be together there, but at least you get a separate package for each module. The next step up that you could do is use your build tool, like Maven or Gradle, where you would use a different Maven module for each actual module in your application. This would produce a different jar. It would still be part of the same top-down build with the same version, and it would end up in the same application at the end. But you do already have the possibility to kind of separate things a little bit further there. If that's not enough, you can look at splitting code out in a separate repository, maybe versioning it separately and consuming it with a fixed version in your application. And if that's not enough, then you can move on to the next step, which is really having some external service that you will call over the network, where you can then really this can be written in a different language, it can be fully separate. And if we kind of draw the line here between Monolith and microservices, we see that it's not, again, binary. We have a spectrum of choices available, where you can really, depending on the situation that you have, when what makes sense, really pick where you want to go on the road from the left to the right. Where it really makes sense to start left and evaluate, is that good enough for me? Fine. I don't need to take any additional complexity on board. If it is not, move one step to the right and ask the same question again, and keep moving until it makes sense. Just don't take any complexity on board that you don't need. Now, the separate repository thing, we'll look at it a bit more in a second, but this is really something that is quite powerful for reuse also. If you have things that are maybe not directly related to business logic, but are closely related to technical infrastructure or some utilities, these are great things for sharing, where you can just have them with a fixed version in a separate repository, maybe being reused by multiple applications, and they have their own life cycle there, just like you would treat any other library. Now, if we kind of look at our two choices here, which involve our build tool and modularity at that level. The very nice thing of having something like that is that we already have some important isolation taking place. We have restrictions at compile time as to the visibility of certain types, so we can already avoid some of that tangling that we saw before, where we can already guarantee at compile time that we will not be accessing certain things that we shouldn't be accessing. So still no guarantee at runtime, which reflection. You can still get around those things, but at least at compile time, you have some nice advantages of what you can use there. The other nice thing, of course, is that the build tool itself will complain if you have a cycle somewhere between your individual modules, so it will actually enforce the acyclic directed graph. So this is quite nice. And in terms of build performance, it's also quite good, because here, for example, with Maven, you can just selectively rebuild the modules that the module itself and the module that depend on it, and the AMD also make dependent flags. So this is quite nice for just building the subset of your system that has actually potentially been affected by the change you've just made, instead of having to rebuild everything all the time. The nice thing also is that our IDEs have deep understanding for this. So in IntelliJ, for example, it's very easy to generate, to auto-generate a graph of the dependencies with your different modules in your Maven project. So you get a nice overview of how exactly the relationships are between those modules. It's something that's auto-generated, so there is no need to put manual work into kind of drawing those things yourself. So that's quite a powerful thing, again, to see the forest through the trees. Now, versioning. One of the big issues we have is, and we talked about it on the monolith side of things, is avoiding jar hell, or is the problem that when you have dependencies on incompatible versions of the same library, it's very easy to run into trouble. So what can we do to at least reduce some of that pain? The first step really is to do less of it, to really look at designing our systems with less dependencies if possible. You only need that one method from Apache Commons? Do you really need to depend on the whole jar, or could you just copy paste it into your code and not have that dependency? These are really trade-offs you should be making when you look at the cost of introducing too many dependencies and a potential scenario you could be running in. So this is definitely something, the lower the amount of dependencies that you have, the lower the potential to run into a situation like that. Also, when picking a dependency, look carefully at how much it is actually pulling with it. How many transitive dependencies are coming along? There are more and more libraries that are finally adopting a zero transitive dependency stance, which is quite nice because once you consume them, you only consume that library and nothing else. And there are no hidden surprises and no things that could potentially break behind the scenes. So this is actually quite an important criteria when making a choice about which library to take for which solution. This is something that you should be looking for. If that's not possible, if you do have to deal with transitive dependencies, at least do make the effort to enforce dependency conversion. We'll look at it in a second of how you can do that with Maven to make sure that you're actually using the same version everywhere and that you have a build that breaks if that's not the case. And if it's really not possible to use the same version everywhere, you still have tools like the Maven Shade plugin at your disposal where you can then copy the code of an existing library under a new private namespace so that you then avoid the conflicts at runtime. Now about that dependency conversion, dependency conversions. This is how you can do it with Maven. So it's just a little snippet for the enforcer plugin that you can use, where you basically say that you want to make sure that all the versions of dependencies are unique. So this is just something you paste once into your build and you're done, and it will provide you the nice guarantee that if you were to add incompatible or different versions of the same library in different submodules, the build would break and Maven would complain about it. Now, in terms of enforcing which module can actually depend on which other module and which package can depend on which other package, which is quite important if we want to make sure that we do not depend on the implementation of other modules, but only on the API of those modules. Java 9 and 10 now come with a very nice property with the module system where you can actually define all this in a module info file where you can specify exactly what you want to use and what you want to expose to the outside world. Unfortunately, not everybody has the chance to move to Java 9 or Java 10 today. It's quite a big change in terms of compatibility with a lot of open source projects. No, the whole ecosystem hasn't caught up yet. So if you're using Java 8, you're not out of luck. There are some good solutions as well. This is a GitHub project called Cobra cert, and they have a nice little DSL for solving this. So if we kind of look at the rules here, for example, I'm just going to read it out loud. So the payment API may use the invoice API. So they have a camel case notation for package names. So it's kind of it compiles through some magic, but it works quite well. You can use this in a unit test. So it takes just a few milliseconds, and this lets you enforce those relationships very quickly and certainly prevent accidental introduction of dependencies that shouldn't be there between packages. So this is quite a nice, powerful thing. I highly recommend you, if you're still on Java 8, to spend a few hours to introduce this into your projects, because it will really help you enforce the structure at a very low cost in terms of investments. Now, databases. That's it's all nice and well to kind of solve the problem on the code side, where you add nice structure and everything's perfect, but then it's all tangled up in the database, and you haven't really solved anything. So how can we deal with that? So first and foremost, I think the most common type of database out there, let's just check who's using a relational database on their projects. All right, it's hard to count the hands that aren't up, so let's say 95% at least. So if you use a relational database, it comes with two very important properties. The first one is referential integrity, where you actually have some guarantees about the consistency of your data in the database, and atomic transactions, where you can be sure that things are either there or not there. And those are really two very powerful things. If you do give them up, it is not that you will not need them, you will just need to re-implement them yourself. So it's quite nice to have that out of the box in the database system. Now, if we're going to be dealing with databases, I think it's quite important to ensure that each module will only be accessing its own table, so that you avoid the picture that we had in the beginning with the dependencies that go wildly from one module to another. We do not want that. We want nice orthogonality here. And so we want to really have some kind of picture like this, where a module will only be accessing its own set of tables in the database and not more. It also means no sharing of tables between modules. So this is something that's slightly harder to get around with. It requires some thought in how you design the database and how you design the database access. This is certainly something where it's not just a matter of writing straight to a table from a different module, but it's also, for example, including tables from a different module in a join of a query. This is also something you should avoid, because you have to start thinking about, again, if you look at our spectrum of choices that we had in terms of code organization, you want to be able to move to the right, to the next choice up, the minute you need it. And so if you get to the point where you have some kind of module that is really becoming too large or too complex to stay within a modular monolith, and it should be moved to its own service, then you want to be able to move the data with it. You want to be able to move that part of the database with that module. And so if you create unnecessary entanglements in the database, it becomes impossible to do that, or at least it only comes with a major effort to untangle all that afterwards. So you have to be quite careful there. So the joins are really something that you don't have to give up completely, but you have to stick to tables within your own tables or views within your own module. So this is something where you'll probably maybe have to do a query more than you would otherwise do, but this is something that you'll have to do anyway in a microservices scenario. So this is something just that requires some thought when designing all that. The nice thing though is that you can still keep things like foreign keys, because even though you have foreign keys across module boundaries in the database, where, for example, the invoicing table will still depend maybe on a customer ID. This is not that much of a problem, because the minute you want to separate out the customer, for example, you can just take away that piece of the code, take away that piece of the data, and before that you just remove the foreign keys and you're done. So you lose the guarantee of referential integrity, but there is not a huge effort required to untangle it. But as long as you don't have to, you can keep the referential integrity and all the benefits it provides. And you can keep having ACID transactions across modules as well. You do not need to give this up prematurely. So you end up pretty much with a picture like this, where each module has its own well-defined API, a private implementation that will be accessing its own set of tables in the database. Now, in terms of grouping those tables and objects, again, we have a spectrum of choices at our disposal. The first and most basic one, of course, is if we have different modules, we don't put all the data from all the modules in the same table. We have a separate table per module. But the first step up from there is really something that's built into almost every database out there today, is the concept of a schema, which is nothing else than a way to logically group objects within a database. And so this is really something that is something that I highly recommend you to go down that path, at least very quickly, is to have a separate schema per module. It's very nice isolation. It's comparable to, let's say, a package probably on the JVM side. It's lightweight. You can still do all the joins. You still have all the referential integrity available, but you have nice namespace isolation at your disposal. If that's not enough, the next step up is to actually have a different database, still based on the same technology, so you can reuse the knowledge in-house, you can have all the expertise that you've built up that is still applicable there, but in a completely separate database, if just having a separate schema per service is not enough anymore. And if you reach the limits of that, if you really say, you know, the relational model just doesn't work anymore for this, we really need a very fast key value store for this, then the next step up would be to then finally move to some kind of polyglot persistence model. So again, here we have a spectrum of choices. Again, start on the left, look if it is sufficient for you. If it is, stay there, don't take any additional complexity on board. If it isn't, one step to the right. Evaluate again, is it sufficient for you? Yes or no? If not, one step to the right, and so on. So if you look at these different possibilities there on our spectrum of choices, the first two there, if you use a database migration tool like Flyway, would typically have the same life cycle. Like the schema would have, or the whole database would have the same life cycle, because you still do want the referential integrity, you want to maintain all those nice properties, and so this would mean, if you're using Flyway, that you would have a single Flyway schema history table to maintain the history and the audit trail of changes that will happen to that part there. So those are just kind of a bit of guidance of what makes sense there in terms of life cycle. Now, scaling is another big argument you often hear from microservices, where you can take an individual service, scale it up or down as needed, no need to kind of move to the rest. But if we kind of look at scaling and think in terms of bottlenecks and where we really hit limits, those limits have really shifted over the last few years. Because if you just look at the range of instances available on demand on AWS these days, on the one hand, you have a T2 Nano, which is the smallest one with one virtual CPU and half a gig of RAM. And then you have a whole range of choices, all the way to the largest instance they have available today, which is the X1E 32X Large, which has 128 virtual CPUs and 4 terabytes of RAM. That's with a T and not a G. It is really enormous, the range that you can go with scaling up. So you're very unlikely to be hitting the limits of scaling up. But even if you do with your a modular monolith, that's not the end of the road, because you can just deploy more of those. You're not stuck to one instance. You can have multiple instances available for running your service behind the load balancer. And so it is very, very unlikely that you're going to be hitting any kind of scaling bottleneck in terms of scaling up these days. But, of course, not everything maybe needs to be scaled up at the same rate. You have certain parts of your application that may be in need of more memory or more processing power than others that should be scaled. So they should be scaled more asymmetrically from each other. Again, here, if you're in a modular monolith, plenty of choices. The first thing you can do is have different executor service with different thread pool capacities, for example, so that if you have something that deals with payments, you will assign it a certain number of your threads, which will be then most likely mapped to your virtual CPUs. And if you have a different service that needs more compute capacity, just size the thread pool a bit larger. And then these two will have a different amount of compute capacity available. Now, if that's not enough for dealing with a load, or you need something more persistent in terms of queuing up work, the next step up you can do from here, again, but only if the complexity warrants it of your requirements, is having a queue in the database. A queue in the database is often, ooh, don't do that. Well, think again. Maybe it's not such a bad choice for the load and for the use case that you have. It's actually quite powerful because you get all the benefits of the database, including participating in transactions, so that you can have very nice guarantees that if you commit a message to the queue, it's also, the other data is also nicely committed to the table. So how does a queue like that work? Well, in its simplest form, it's really just a table where you would have something like an ID of an individual message, and then the message payload itself. To add things to that queue, pretty easy. You just insert into that table. The ID is some kind of auto-increment column, so it gets auto-assigned, and you just push a new payload, and it gets a new ID, and you're done. Now, if you want to consume something from that queue, it's actually not that complicated either. This is some syntax from Postgres. It's available from the 9.5 onwards, or 9.6, I'm not sure anymore. And basically, it allows you to have something here which is quite powerful. You open a transaction. Within that transaction, you issue a delete for the message that you want to access. And so how do you select the message? You will select the first one that's available. So you select the ID of the message. You only return one record. And then the clue comes. You select it for update to take a lock on that row. And you skip the rows that are already locked. So if the first 4 rows are already locked, there's no wait time. You just go straight to row 5 and grab that, and you return the contents of that record. You return the payload, you return the message, and now you do your work as usual. And if it's successful, you simply commit the transaction. You will have the changes in your database, and the delete will be performed in the queue. If, on the other hand, you're not happy or there's some kind of error, roll back, and the delete operation is rolled back, and the message is back in the queue, and nothing has been written to your database. So quite simple, quite powerful, and more than sufficient for a lot of use cases. But if that's not enough, again, next step up, a dedicated queuing system can be something that's very fast, very highly available, and can be a fantastic solution also within a single application, where one module writes to the queue, the other one reads it, perfectly fine. It doesn't need to be different applications on the producer and on the consumer side. Now, having the ability to write microservices in the language of your choice is something that is often presented as a very strong advantage. And we are very lucky with the platform that most of us use, with the JVM, to actually have had the teams at Sun and later Oracle put in the effort to actually make something like that possible on the JVM side as well. So we actually have lots of languages these days that will run on the JVM, and with stories like Kotlin, where you have perfect interop between Java and Kotlin, you actually have the choice to write the module that you want in the language that you want, and they'll be able to interact with each other no problem using the interfaces and the APIs which we talked about before. So this is actually something that's very powerful, very easy to do these days. So you do have the choice to pick the language that you do deem to be the right choice for each module there as you wish. Now, when it comes to actually deploying your modular monolith, this is the 1 minute shameless plug for the work that we do. So if you want to deploy it to AWS, we offer a service there called Coldbox Fuse, where you can just with one command do box fuse run, and then your application, and it will basically provision everything for you. All the infrastructure will be up and running in minutes, so it will auto-detect what kind of application you have. It will provision databases, load balancers, security groups, everything that you need. It does zero downtime updates of those things as well. It's based around immutable infrastructure and infrastructure as code, so it really allows you to fully describe what you have and store it in a configuration file and not needing to do anything there. So it's also based around minimal images. We generate the smallest possible operating system that your application needs on the fly, and we create a new AMI from that, so you have the guarantee that it's that what you deploy is 100% identical between all environments with very low complexity, letting you focus on development. And if you have changes to make in the on your relational databases, that's my other shameless plug. It's Flyway. This is really, you can think of it as version control for your schema. It is based around plain SQL, so there is no proprietary language or dialect to learn there. It supports all the popular databases out there. Last year there were 4.3 million downloads, so you're by no means an early adopter. If you start using it, it was designed for continuous delivery from the start, and it comes in multiple editions. There's an open source community edition, and we do offer commercial, pro, and enterprise editions with additional features and guaranteed support times. So this is, again, a highly focused tool, very easy to get started. In 5 minutes, you can get it up and running. So if we summarize what we've just seen here today, I really think that Majestic Modular Monoliths provide a very nice middle ground, which can be a fantastic choice for a lot of companies that do not have the thousands and thousands of engineers in their, on their payroll, but instead it offers you a way to combine the simplicity of monoliths with the structure and focus of microservices. So this is really something that is that should be evaluated and looked upon whether it makes sense or not for you. You've seen for all the individual parts of it, there is a spectrum of choices. Pick the simplest thing that could possibly work, or as we could say as well, go modular and make your monolith majestic again. Thank you very much for your time.